Team, third video. I'm getting a little bit exhausted with the videos, but no, I'm doing it for you. So let's continue on with conservation of angular momentum. Conservation of angular momentum. And in this aspect, it's the same thing. It has to be a closed system, like in the conservation of momentum. It has to be a closed system. And it also has to be an isolated system. But just like in isolated, when it comes to rotation has to do with torque instead of force, right? So instead of all the sum of all external forces is equal to 0, it's the sum of all external torques is equal to 0. So you will see two different types of conservation of angular momentum. The first type is the conservation of angular momentum when it's a straight line. So let's say that this is a bullet, right? And this bullet is going in this direction. It has a mass, it has a velocity, a directional velocity in this direction, right? But with respect to an origin, a point of origin, even though it has momentum, a linear momentum going on here with respect to this point of origin, I'm going to try to line this up right here. With respect to that, it means that it does have angular momentum with respect to a point. So with respect to a reference point, okay? So that's extremely important, and that can be rewritten as angular momentum is equal to r, the distance from the object to the reference point, times p, which is momentum, linear momentum, okay? If there is an angle given, like, look, this one in itself is very explicit that has a vector too. So we have a vector of y. Let's say that this is r, this is a vector r, and this has a vector of rx. Okay? You have to make sure that when it comes to momentum, just like torque, remember that torque has to be perpendicular like this. Remember this equation? If you don't, well, I'm sorry. But this is the equation for torque. And this also has to be perpendicular to the axis of rotation. In this case, ry would have to be perpendicular to ry. So you would have to find the component of ry in order to find the momentum or the angular momentum of this bullet. Okay? It has to be perpendicular. So let's say this is momentum, mv. It has to follow a 90-degree angle in order to be multiplied. And you can find this, you can rewrite this as angular momentum is equal to r times mass times velocity sine of theta. Okay? Or it just depends on, like, let's put it this way. If this is angular momentum, right? Or let's just write it like this. If you have a direction, this is your R value, but your momentum is going in this direction. It is not completely perpendicular. So you're gonna have to find, let me write more MV. You're gonna have to find the vector that is perpendicular to the distance from the point, from the origin. And that's gonna be mass times velocity times r, right, times cosine of the angle here. So now you find mass times velocity cosine of the angle, and you have a multiplication where you can have the perpendicular. It is the mass, the momentum times or perpendicular to the distance from the axis of rotation. Okay? Now, we spoke about linear momentum with respect to when it comes to, or angular momentum when it comes to a bullet or an object that is linearly moving, and it still has angular momentum due to the reference point. But objects that rotate usually have momentum too. So most easiest thing to put is like a sphere. But an object that is rotating has moment of inertia, and it also has, since it's rotating, it has an angular velocity. If you want to find the momentum, you will multiply the moment of inertia of that object times the angular velocity. And depending on what the object is, like if it's a spherical shell or something like that, you can find it on your PRC and replace the spherical shell equation or moment of inertia with 2/3 mr squared, which is the equation for a rotational inertia of a spherical shell. And this is just an example. But this is how you find the moment or the momentum, the angular momentum of a rotational object. Okay, so let's talk a little bit about the summation of the initial angular momentum, which is described as big L, equals the summation of the total final momentum, which is also big L. Okay? And what does it mean? So let's say that, very simple example. Let's say that there is a bullet heading into a spherical shell or something to that effect. And this spherical shell is already rotating this way, right? This bullet is going at a certain velocity and a certain mass. Okay? Given that we're taking into consideration this is the reference point where it's the center of the spherical shell, this bullet has an angular momentum. Now, when it comes to angular conservation of angular momentum, always remember it is right before impact and right after impact. So right before impact, tick, 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 it is right here, right before impact, right? And this distance is r. So check this out. This has a momentum, and it has a perpendicular to the distance from the axis of rotation right here. So this is right before it impacts. So we can rewrite this as mass times velocity times sine of 90. Remember, it doesn't, like, as long as you identify that it is 90 degrees, you know that that's fine. It's complete, like, you don't even have to write this again. It's just mass times velocity times the distance from the axis of rotation because it is perpendicular. That is the only way that you can actually get an angular momentum, as long as they are perpendicular to each other. Okay? So another, just rewriting mass velocity, and then this is, and this is r. All right? So we rewrite this as this. Now, since the sphere or the spherical shell is already moving, you can rewrite it as moment of inertia times angular velocity. Okay? So notice that it has the different components. So this is the moment of inertia once it starts rotating. But this, okay, so this is the moment of inertia or momentum, angular momentum of an object that is rotating. But on an object that is in linear motion, but it has a reference point like this, you can still account for the angular momentum, but this is the equation that you write it as. Okay? Now, afterwards, these two are together and they hit right here. Now they are together. Now the bullet is a part of the system. So you can rewrite this, since it's a part of the system now. The final angular momentum can be rewritten as the momentum or the moment of inertia of the bullet plus the moment of inertia of the spherical shell. I'm going to abbreviate it as S, times the final angular velocity. So, let me rewrite this as initial. So, now it is treated the same way as when you were doing the conservation of linear momentum, but now you're summing up the this rotational rotational inertia for both. Now, a bullet, and I cannot emphasize this enough, do not forget that little small objects or like something that is introduced that is like in a circular shape, you can read it, like you can consider it as a point mass times r squared. That is the rotational inertia of an object that is just a point mass. Once it is rotating, once that object, the bullet is rotating, it has rotational inertia. So that's why it is no longer written as mass times velocity times r. It is written as the rotational inertia of the bullet times the angular velocity. Okay? So that's why we introduce it as rotational inertia. Okay, from here on forward, all you have to do is replace these with, so mr squared for the bullet plus 2/3 mr squared for the spherical shell times angular velocity. Okay, and voila, you found the final and the initial angular momentum and the final angular momentum. Now you can, whichever they ask you, like, you can solve for in that respect. Okay, so that is the basic concept of conservation of angular momentum. So let's hit on TP11-58. I'm sure you guys are fans of TP11-58. So let's do TP11-58 for your viewing pleasure. So we have givens. Let's write down the givens. Mass of the particle, velocity, moving at a velocity. Particle is moving at a velocity, so we're given that. And then it collides and they stick together. Extremely important. So that means it's in an elastic collision. They collide, stick together at the edge of a uniform solid cylinder. So we know that this is a uniform solid cylinder. We have to find the moment of inertia in the PRC for that. Okay, cylinder is free to rotate about its axis and is perpendicular to the page. The cylinder has a mass. Okay, so we have the mass of the cylinder, and the radius of the cylinder, and what is the angular velocity of the system. So we have to find the angular velocity of the system given these components. System. Okay, so first thing, tackling this problem, physics. Boom. Rewrite this, or write this as the sum. When you see, well, first of all, when you see that there's rotation involved in this, and it's asking the angular velocity of the system, it's like, and there's collisions involved. Like, notice the words collisions, angular velocity. It's like uniform solid cylinder. boom, this is definitely a conservation of angular momentum problem. So make sure you write down the sum of all initial angular momentum is equal to the sum of all final angular momentum. Okay? So you write this down, and you also write down that angular momentum is equal to r, the distance from the axis of rotation, times the linear momentum p. And you can also write as L, another way, when it actually is rotating, rotational inertia times angular velocity is also rotation. It's also angular momentum. Okay, so we have those equations for you to identify. And like, okay, so like this again, like it's always important to write down the equations, because we care the most. The thing that we care the most is that you can identify what type of problem is it. Okay. So the next thing that we do is identify a coordinate system. So we have our coordinate system, which is x and y, and once the bullet hits, we have the impression that it's going to rotate in this direction. So we're going to put that as, if it's rotating in clockwise, then it is positive. We have the ability ourselves to decide what is positive, what is negative. We could also decide that clockwise is negative, but it's just simpler to go in the direction of motion like we've always taught you. Okay? Now, let's think about what happens before and what happens after. So let's write the equations out for final, initial, and final. So initially, it's saying that the cylinder is at rest. So there is no moment of inertia occurring in the cylinder because the angular velocity is 0. Okay? But there is a particle that's about to hit the cylinder. And remember, always remember, this is kind of like fooling you, because you would think, oh, but wait a minute, the distance is actually kind of weird, because the distance from where it's hitting, from where it's at the page to the axis of rotation, it's kind of like have an angular effect, and I'm not really sure what the distance is. Don't confuse yourself. Just think of it this way. We only care about what happens before and after. So right before, like right here, when it's actually like completely perpendicular to the axis of rotation, so you can consider this a way to like, okay, so this is good because this complies with mass times velocity, the cross product of r. Okay, this complies with that. So right before, right there, it hits. Right before it hits, it is 90 degrees from the axis of rotation. So that's perfect. We can write this as mass times velocity times r times sine of 90. And that sine of 90 is 1. So boom, we are done with identifying everything that happens at the very beginning, right before of the impact. So now we have to identify right after the impact. And right after the impact, what happens is, now we have both in the system. We have both the particle and the cylinder moving, and they all have rotational inertia, because the particle is now a part of the system and it is rotating. That is the key. Like, the particle wasn't rotating before. It was a linear motion, but considering it in the reference point of the center of the cylinder, it still had an angular momentum. In this situation, the particle is rotating with the system itself. So we write down moment of inertia of the particle plus moment of inertia of the cylinder times the final or the angular velocity of the system. Okay, so this problem is almost in the back. So we rewrite this as mass times velocity times r, because sign that goes away, and we've already identified that the direction in which it's going is also positive, so we don't have to worry about any negatives, is equal to, now we can switch this, the moment of inertia of the particle, into an actual equation. The moment of inertia of a particle of a point mass is mass of the particle times radius squared, plus the moment of inertia of a solid cylinder, and I'll just check back in my PRC just to double check. PRC, cylinder, solid cylinder about the central axis is 1/2 mr squared, plus 1/2 mass of the cylinder r squared, because they both have the same radius. Because the particle is at the edge of the cylinder, they both have the same radius when it comes to the movement of the object, or when it comes to the moment of inertia of the object, of the system. And we have the angular velocity of the system. Boom. So now it's saying, what is the angular velocity of the system after collision? Too easy. Now you can bring this component onto the other side, m, which is mass of the particle, and I forgot to write that, mass of the particle times velocity of the particle times r, over mass of the particle times r squared, plus 1/2 mass of the cylinder r squared, is equal to the angular velocity of the system. Voila. So you are done with part A, finding the angular velocity of the system. Okay? It's very, very specific, very straightforward. So then it's asking you how much kinetic energy is lost in the collision. Okay. Remember what I talked to you about in the previous videos, video that was really Hispanically, videos, about the conservation of energy. So this has to do with conservation of energy. If you just set it up the same way, you identify the final mechanical energy minus the initial mechanical energy, you will find that it is very straightforward. So let's identify the initial mechanical energy. Okay, so we have velocity and we have mass of the bullet. The bullet is the only thing moving at the time. And remember, the bullet, it does not matter about direction. It is path independent when it comes to kinetic, when it comes to energy. So all we have to do is identify that the only thing moving at the time is the bullet, and it has a translational energy, mass times velocity squared. Mass of the particle, and I keep saying bullet, but it's actually particle, I'm sorry. It is particle, mass of the particle, velocity squared. So we identify the mass of the particle, velocity squared, and there's nothing else going on. However, we do have, like right at the end, kinetic rotational energy. So this is kinetic translational because that is the only thing doing. Then we have at the end kinetic rotational energy, and that can be 1/2 the moment of inertia of the particle plus the moment of inertia of the cylinder, angular velocity squared of the system. So you found the angular velocity of the system, so now you can include it here. This is, and don't be scared, by the way, this is in your PRC listed as, and let me just pull out the PRC just to show you a reference here. PRC, and if we look at the energies, oh, there it is, kinetic rotational energy. So in this respect, we're summing up the moment of inertia of the particle and the moment of inertia of the cylinder, because that is the moment of inertia of the entire system. Remember, so now, because just to not confuse you too much, remember now, like for this, it's the entire system, it's the moment of inertia of the particle plus the moment of inertia of the cylinder. Okay, so that's why we have this right here, because we're taking into consideration the moment of inertia of the entire system. Okay, so now all we have to do is equal them. So this is the final mechanical energy, and this is the initial mechanical energy. We sum all the components, but there's only one, so we go 1/2, and I'm just gonna write it, the moment of inertia of the entire system times angular velocity squared, system squared, minus 1/2 mass of the particle velocity squared is equal to work due to non-conservative forces. So the energy loss is actually what you're gonna get once you subtract these two together and you get a value here. That would be the loss of energy of that system once they collided together. Okay? Oof. All right, give me a second. Let me take a break. Okay, so now we're going into another problem, and this is for your own learning. This would be good for you. This is actually a problem from the supplement. Okay. So look at your supplement on the course website. You should see it in the course lesson of conservation of angular momentum, and click on the course supplement. You should see this problem. Okay. This is just to emphasize the importance of why it needs to be in a perpendicular way. So I'm giving you a second to read the problem. All right, so mass, we have mass. Let me write givens. Okay, givens, we have mass. Holding medicine ball. Okay, medicine ball of 50 kilograms, 5 kilograms right here, is standing on the very edge of the merry-go-round, which is modeled as a solid disc. Okay, we have a radius, which is 1.5 meters. And then we have a mass, which is the solid disc, which has a mass of 150. The merry-go-round is rotating counterclockwise, well, that's important, as viewed above, on a frictionless bearing at an angular speed of 1.17 radians per second. The goal throws the ball of the merry-go-round at the angle of 120 to the radius of the direction opposite the rotation to the merry-go-round. So don't be scared about there's an angle, it's 120 dots. Settle down, give me a second. So just look at it this way. You have to put it perpendicular, right? So you have to find the angle right here, 120. This is 90. This is 90 degrees right here. So 120 minus 90 is 30 degrees. And since this is right here, this is the magnitude, this is the hypotenuse, and this is the adjacent hypotenuse, and this is the adjacent. It means that we can find the actual angular momentum by just using cosine of 30. Well, I digress. Let me continue with the problem. Calculate the speed of the ball after the girl throws it. Okay, so I left a lot of the components here just because I wanted you to see what's happening before and what's happening after. So notice, this time it's not that the bullet is about to reach the system, and this time is that the system is throwing out something, and we have to consider the momentum after that ball is thrown out by the little girl. Okay? So, again, we have a physics, final equals the initial. And then we start writing it here. So we write initial angular momentum plus the final angular momentum. So let's consider everything that's happening at the very beginning, just before. So we have, there is motion involved and there's a system. So the entire system itself is moving. So that is the angular velocity of the entire system, the initial velocity, the initial angular velocity. But we also have to consider the moment of inertia of the things that are going on within the system. We have the mass of the girl. Let's consider the mass of the girl as a point mass. Okay, so let's consider the mass of the girl as a point mass, and let's consider the mass of the ball as a point mass as well. So we can rewrite this as mass of the ball, or the moment of inertia of the ball, plus the moment of inertia of the girl, plus the moment of inertia of the solid disk. So I'm going to plot it as solid disk. Okay, so we have the moment of inertia of the ball, the moment of inertia of the girl, and the moment of inertia of the disk. So notice that this is everything that's going on within the system. Nothing has left the system, and that's where we have to include it all together. They're all moving at the same angular velocity. Okay, so that equals to, right after they leave, we now have a system that has the girl and the cylinder and the solid disk together. So we have the girl, the moment of inertia of the girl, plus the moment of inertia of the disk, and it has a final angular velocity, as you can see here. And it also gave us a final angular velocity. So that's fantastic. However, the ball escaped. Oh no, the ball was thrown out. But not to fret. Remember, everything has to be perpendicular to the axis of rotation. So even though it has an angle, it just basically means that we have to now switch this up and say mass of the ball times velocity of that ball times cosine of 30. Remember, this right here, I'm going to put it right here. This is a bad drawing. This is 120. And this right here is 90 degrees, where we want to be at. We want to be at 90 degrees. Let me take this 180, put it right here. Okay, so all this is 120. I'm going to put it highlighted in red. 120 highlighted in red. And we want to make sure that the angular momentum, where the momentum is perpendicular to the axis of rotation. So the axis of rotation is right here. Okay? What we need is this angle right here. That angle is 30, because 120 minus 30 is 90. Okay? So, no, 120 minus 90 is 30. So that's what we want, the 30-degree angle. That's why, in order to turn it perpendicular, the moment of inertia perpendicular, we have to multiply by cosine of 30. And this is also times r, which is the distance from the axis of rotation. Okay? That is the reason why we multiply by cosine of 30. You have to turn it perpendicular, like if there's ever an angle like this. Okay, so we identify the initial and the final, And now all we have to do is convert everything into what we are given. So we were given mass and we were given the radius. So mass of the boy times radius plus mass of the girl, not the boy, mass of the ball times the radius squared, mass of the girl times radius squared, plus mass of the solid disk, PRC, just to verify. Solid disk, here we go, 1/2 mr squared. Yep, mr squared, which is 150 kilograms, mr squared, times initial angular velocity is equal to mass of the girl now, r squared, plus 1/2 mr squared times final velocity plus r mass velocity cosine theta, cosine 30. Now, I forgot one very important thing that you might be angry with me about, and I apologize, but I noticed that I completely forgot to identify the coordinate system. So it's saying that counterclockwise in this respect is positive. So we identify that. Okay, so this is positive. Good. This is positive. The initial momentum is all positive because it's going counterclockwise. Now, in the second part, when the final one, yes, the final angular momentum is still positive, but this takes a turn because now it is going in the opposite direction. It is going in the opposite direction. The momentum is going to be negative. So let me erase this. And this time it's going to be negative because it's going opposite of the rotation. Okay? So that's important. And now the question was solve for the velocity of the ball right here. So now all you have to do is solve for the velocity of the ball. I'm not going to do the math for you. This is a lot of math, but velocity of the ball is equal to, you're already given mass of the ball, mass of the girl, mass of the cylinder or the disc, radius. You're given the initial angular velocity, and you're also given the final angular velocity. So really, all you really need to do is plug the numbers and solve for the final velocity of the ball. Remember, always in a WPR, always attempt to solve, even if you don't know how to get there, at least show us that you know that this is, you have to solve for this specific thing that we're asking you to solve for. Okay, so at least you get some credit for that, okay? But team, I think that's it for conservation angular momentum. This was a very long video, and I hope that you enjoyed it.